magic here is that instead of knowing the probability in advance, what I'm doing is I'm replacing the probability with my, let's call it the universal probability Q. So use Q instead of the true probability. Now, what did I do in order to get the arithmetic code word? So remember, an arithmetic code is basically a Shannon-Fadden-Elias code, and the idea there is we have the cumulative distribution function like so, and what we're really doing is we are finding this function f bar of x, which is the cumulative distribution function is f of x. F bar of x, if I take these vertical intervals, f bar of x is the halfway point of each of these intervals. So we've shown that this produces, if you know the probabilities, this produces a code that performs within 2 bits of entropy. So what I do is I get f bar, and then I encode with ceiling log 1 over p of x plus 1 bits. In other words, I take the binary expansion of f bar and encode with this many bits. So nothing really changes here, except that in order to get f bar, what I'm doing is I'm using q instead of p. So how did I get f in the first place? Well, for one thing, we notice that f bar is equal to f of x minus 1/2 p of x. Why? So these vertical intervals, the level for each x is f of x. And the size of this interval is p of x. So halfway up this interval is clearly f of x minus 1/2 p of x. Over here we can immediately substitute f of x minus 1/2 q of x instead of p of x. Now the only difference is, how do we calculate f of x from q instead of p? Well, exactly the same way, except we're substituting q for p. So probably the easiest way to see how this works is to do an example. So remember this trick. If the source is binary, f of x equals, we have f, x1, x2, x3, and so on up to xn. What is f? It's the probability that the random variables x1, x2, x3, and so on up to xn, now these are capital letters representing the random variables, are less than or equal to the specific values lowercase x1, lowercase x2, and so on up to xn. So, we can deal with the less than case first. Firstly, if the most significant bit is less than the most significant bit over here, then the entire sequence must be less. So that's the probability that x1 is less than little x1, the specific value. The most significant bit is less, clearly the entire sequence must be less. Plus probability that this is equal, and the next most significant bit is less. first 2 bits are equal, and the third bit is less. This is similar to, if you think about it, this would also work in decimal. So if I had, remember our interpretation of this sequence was as a binary fraction. So if we had a decimal fraction, 0.9367, then firstly, the first position, so if I had probability dot decimal 1, decimal 2, decimal 3, decimal 4, less than or equal to 0.9367, this is the probability that, okay, clearly if D1 is less than 9, anything that starts with something less than 9 must be less, plus the probability that D1 is equal to 9. So anything starting with 0.9 could still be less if the second digit is less. Anything starting with the first 2 digits, 9.3, could still be less if the third digit is less. And so on. So that's the fundamental idea over here. Now, that's fine until we get to the end. So plus and so on, plus probability x1 equals x1, and so on up to xn minus 1 equals xn minus 1, and then xn is less than little xn. So that's the natural continuation of this sequence. But then I also need, so these terms together comprise the less than case, and I also need the equals case, plus probability x1 equals x1, x2 equals x2, and so on. xn equals xn. But this last term here is actually equal to the probability of the sequence. So how do we adapt this to our universal probability? Once again, I will write qn plus 1, excuse me, q xn plus 1 given x1 to xn is equal to kn plus 1 divided by n plus 2. That is that's our fundamental, the fundamental building block. And let's try to encode. What we're going to do is we're going to encode 0, 1, 0, 0, 0, 1. So firstly we get f of 0, 1, 0, 0, 0, 1. That is equal to probability that x1 is less than 0, plus the probability that x1 is equal to 0, x2 is less than 1, plus probability that x1 is equal to 0, x2 is equal to 1, x3 is less than 0, plus the probability that x1 equals 0, x2 equals 1, x3 equals 1, excuse me, x3 equals 0,